Okay, any question or comments on the last lecture?
Sir, you use the word antiquity.
Antiquity.
So there were two references. One was saying it is 476 to 1492, and the other was 8 BC to 5680. So
Antiquity is anything that is old and long time ago. There's no fixed duration. Sometimes maybe you're talking about something recent, and from antiquity you may mean like 200-300 years ago. And let's say yesterday, since we were talking, we started that historical debate around 500 BC. So in that context, antiquity meant, let's say, 2,000-3,000 BC. So it's a relative term. Okay. So in the last lecture, we discussed the debates that were going on about the nature of light. So let me just give a few sentence summary of that. So initially, people thought that it's made of particles, and that point of view was prevalent for quite some time. But starting with Descartes, that particle view was that the ether that is present everywhere in the universe, it's made of particles, light particles, and those particles exert pressure, but they don't actually move. So that was one view of corpuscular theory. The second view was what you can say can be attributed to Newton, even though he was not that much of an anti-Arian. It is that in that the particle actually moves like in a string. So for the first view of particle, you need a medium. For the second view of particle nature of light, in which light is a string of particles, you don't need any medium for light to propagate. Because these are particles, they can even go in sort of quote-unquote empty space that doesn't have anything. And that view, the view that was started from Descartes, that there is an ether with particles that exert pressure, that was refined later, that initially it was thought that the particle undergo vibratory motion like sound waves, but they don't actually move. So that view converted into a wave phenomena. And later on, it was discovered that it's not a longitudinal motion of ether particles, but it's a transverse motion of particles. So, but that particle thing went away. It's just, you can imagine maybe a continuum ether which is vibrating in transverse direction, and wave is propagating this way. And the view was further refined by Maxwell when it was postulated that it's essentially electric and magnetic fields that are vibrating, and the wave is propagating, and it was assumed that for this propagation there has to be a medium because it's a wave, so something has to be oscillating. So for that something, there was a hypothetical medium. So the two theories differed in this way, that for corpuscular theory, the later corpuscular theory, you don't need a medium, and for wave theory, you do need a medium. So I will actually come back to this ether concept later in the lecture today, that why it was becoming even more important, and its implications were beyond light as well. Because if you imagine there's an ether, so it's permeating all space, then it's reasonable to assume that it is stationary in some absolute frame of reference. So assumption of ether leads to an absolute frame of reference in which you can measure velocities of other bodies with respect to the background ether. So the detection of ether became important because it could either lead to the presence of an absolute reference frame, or it's that we have to discard that idea of absolute reference. So it has an effect on the principle of relativity as well. So we will come to that point later. What I want to discuss today is the debate about the velocity of light. That actually came to a definite conclusion within the experimental era. So this debate is, I would say, much easier to follow than the debate about the nature of light. So it's not surprising that majority of people in antiquity assume that speed of light is infinite. Because speeds in those days, what you can compare the speed of light with? You can compare the speed of light perhaps with birds or maybe people running, the fastest runner probably, or maybe horses. So, and actually for all perhaps practical purposes, it's infinite with respect to that. But slowly people started to attribute more philosophical reasons to why velocity of light has to be infinite. And one of the earliest explanation was by Descartes, that since whole space is permeated by ether and light is nothing but a pressure, and this pressure is transmitted, so since nothing moves mechanically, this thing can move with infinite speed. So Descartes was of the view, and actually many people, that velocity of light is infinite. And again, it turns out that Alhazen was the person who argued that the velocity of light cannot be infinite. You can read chapter 1 to follow his exact sequence of argument, but it goes like this. He says that if you have a light source, and you have an aperture here, and let's say you are looking at the light source from here. So he argues something like this, that if you close the aperture, of course you don't see it, but as soon as you open the aperture, you see the light. So this, he says, means that velocity of light is finite. How? Because he says that once the aperture is closed, let's say light is coming until this point, and it's not going beyond it, but once you open it, the light comes from this point to this point. So since this is something that goes in space from one point to another, the speed has to be finite. If we can attribute things like this, that this thing goes from here to here, it means it goes with finite speed. It may be very large, but it goes with finite speed. So he kind of philosophically argued for the finiteness of the speed. And actually several other scientists at that time, especially the famous one like Avicenna, they, of course, they agreed well with Alhazen.
So what if the time? Alhazen didn't measure the time, right?
He did. So he postulated from this thing. So he's not arguing anything from experimental point of view. Of course, this is one weak point, that maybe it takes zero time. But that's his argument, that if things go from, in space, they go from one point to another point, they can only go in a finite time. So that was his argument. But the first serious attempt to measure the speed of light, and at least to give the idea that how you can measure speed of light, was actually given by Galileo. His experiments were not Galileo conclusive, but the idea remained, and that was used to measure speed of light later on as well. So imagine you are in 17th century, and you want to measure the speed of light. You don't have clocks, like these clocks. At best, maybe you have a pendulum clock that when you have to measure some time, you release it from this and it oscillates, and you can measure the time interval from the number of oscillations. So he proposed that, okay, have two people on two mountains with two lanterns. So lanterns are actually these things where you have a glass to protect the flame from blowing wind, which has a window. So there's another lantern here with a window here to the light source here. So try to keep them as distant from each other as you can, so that both of them can see each other's lantern when the windows are open. So he says that initially, when you are comfortable that they both can see, okay, can you guess what should be the method? To measure speed of light this way. Human? We don't have synchronized clocks at that time as well. Actually, there are no clocks. You only have pendulums to measure time. So you have to make time measurement only on one side. You can't actually do like this, that, okay, this is closed, but let's say you try to measure only time for light to go from here to here. That essentially have other problems as well, but one problem is that we don't have synchronized clocks. That your stopwatch should start when this window is open, and it should stop when the light reaches here, when this person sees the light. So for that, first of all, you need synchronized clocks, and then you need a way to transmit the information of opening of this window to this point. So that's not practical, and he knew that. So he said, okay, let's do this. Both of the shutters are closed, and on one side, this person opened the shutter, but then he also let, let's say, a pendulum start oscillating to measure time. So the job of this person is, as soon as he sees the light from this lantern, he opens his own shutter. And then the job of this person is that when he sees the light from this one, he stops counting. That was his idea. And he actually trained these two people for several months so that they become expert at this opening and closing of shutters exactly when they see the light. So he trained them for a long time and refined the clock measurement, and then they tried. I think they have a distance of a couple of miles between the mountains. But actually his experiments were inconclusive because he couldn't measure the time beyond the human response time. That sometime it was, let's say, he opened it, and it just only takes as much time as you take the time to open and close. So at the end he concluded that speed of light is extremely large, if not infinite. So that was his conclusion. So he didn't actually exactly say that it is finite because he wasn't able to measure it, but he did say that even if it is finite, it's extremely large. But his idea that to measure speed of light, you have to measure the round trip time that was kept and used later. So after this, so actually Galileo and Descartes were contemporaries. So let me give you another argument of speed of light to be infinite by Descartes. So he was the proponent of infinite speeds. And right about after him, since Huygens was proposing that light is a wave phenomena, and when you say it's a wave phenomena, it literally has to have finite speed. Because in the wave phenomena, something moves and then wave moves. So the proponent of wave nature of light, they were in favor of finite speed, even though they don't have any measurement. So one of the arguments of Descartes was this, and I want to show it because to let you know how people have struggled with different things to understand nature. That he says that at the time of lunar eclipse, and lunar eclipse happens when shadow of Earth falls on moon. When these three are in line, you see sunlight can't reach moon, so moon gets darker, either fully or partially. So that's lunar eclipse. So he says that if speed of light would have been finite, and he says assume that light takes 1 hour to go from Earth to moon, and of course 1 hour to get back from moon to Earth. So if the speed of light was finite and assume it takes 1 hour, so by the time we see the eclipse, moon would have gone here, right? So when it came under shadow, it took 1 hour for this shadow to reach there, and 1 hour for that information to come back. So in 2 hours, the moon must have traveled considerably. So our telescope should point in this direction. And in those times, astronomy was actually quite advanced, where even though it's night, because you see moon during night and lunar eclipse more clearly, people knew that where the sun is, even though you can't see the sun, because once you have measured the speed of rotation of sun, you know even during the night how to continuously move your telescope so that maybe its backside is pointing towards sun. So he says that, but when we observe lunar eclipse, the telescope is still pointing opposite to the sun. So this is, he says, what actually happened when we see lunar eclipse. But this is what should happen if the speed of light is finite. You get this argument? So you see, let's say this is the telescope, my hand. So before this, even in the night, scientists knew how to know the position of sun. Because our telescope shouldn't point opposite to the sun, but it should point at an angle. And this angle, he says that it takes 1 hour, so it should be quite considerable. So since this doesn't happen, the speed of light is infinite. Can you see the flaw in this argument? Because Huygens quickly saw it.
The earth also moves.
Sorry? So Earth also moves, and your point?
सन की मूवमेंट जो आप बात कर रहे हैं वो अर्थ के रिलेटिव है, तो अर्थ मूव करेगी,
Earth moves or sun moves is the same thing. So, but
मून मूव करेगी.
so actually that should have added even more twist to the story. That even if that would have affected, Descartes would have argued that this slight change that you see is because of the movement of Earth and Sun. But even because of those movements, you still see the telescope exactly pointing opposite to the Sun, which can only happen if the light has infinite speed. Because it quickly is blocked, and at the same instant, you see the lunar eclipse on this side.
So to say, moon, the way we see the moon, we see it only by the light that reaches us. So even if there was a large delay, the telescope would still have to point opposite to the sun to see
No, if there is a large delay, let's say 1 hour, and actually that's something that we'll come to back again when we are discussing the ether speed, but the telescope has to be turned. So actually, Huygens quickly saw the biggest flaw in this argument, and that is that Descartes assumed that let's assume light take 1 hour to go from Earth to Moon. He said, let's say it's only take few seconds. Let's say take 8 seconds, suppose. Then in 8 seconds doesn't move much that can be sensed by the instrument that we have. So he says this argument doesn't hold. So that argument quickly went away. But you see the discussions that keep on going about whether the speed is finite or infinite. Still it hasn't been measured. It's just the argument based on philosophies and the nature of phenomena that people see. Okay, so Huygens said, let's say take only 10 seconds. So in that case, he says the moon doesn't move much, so for all practical purposes, our telescope will still point away from the sun. Okay, so let me now discuss the first measurement, conclusive measurement of speed, which was done by Roemer. I think he was French. So what he was doing at the moment, he wasn't interested in measuring the speed of light. He was an astronomer, and his job was to actually assign longitude and latitudes to different places, I think in France, but you can check in the book if it's another country. And for that he wanted some good time reference, a stable time reference, a stable thing to measure time. And since at that time we don't have anything stable and repetitive on Earth, people had come to know that the moons of planet Jupiter, it actually has 79 moons, Jupiter. Most of them are small rocks, but there are 4 of them that are quite big, that you can consider them to be almost like regular moon. And actually all these 4 moons were discovered by Galileo when he first started using telescope to look at different stars and planets. Initially he was pointing at Jupiter, which is actually I think 3rd brightest object in the sky. And he noticed another star appearing sometime on this side, sometime on this side. So initially he thought it's another star, but because of the repetitive motion, they came to know that it's a moon of this planet. So these 4 are called Galilean moons. And Roemer and people have started tabulating their periods. So the period of this innermost moon, I think, is around 1.7 Earth days. So let's say here is Sun, here is Earth, and here is Mars, and here is Jupiter. So Roemer was measuring the periods of this inner moon, and what he noticed that the period is not constant. And when he is going away from the Jupiter, Earth is going away from the Jupiter, the period is longer, and when at this point, when Earth is going towards Jupiter, the period is smaller. So this was a dilemma initially, and how to explain different periods of this innermost moon. And the difference was big enough to be not ignored. Because when you are doing experimenters know that sometimes you measure the same thing, the value could be slightly different. But you know the uncertainty that can creep because of your instrument. So if the difference is much larger than uncertainty, it means it's something actual. So the difference was perceived actual, and he attributed it to the finite speed of light. And he computed the speed of light. His number was actually roughly 25% off from what is the value accepted today, but it was quite close enough. And his error was not because of the measurement, but his error was because of something else that he, I think, couldn't consider into the speed of Jupiter correctly into the calculations. Because Jupiter is also moving, but other people quickly corrected it, and the value was found to be quite finite, even though it was large. And many people started to accept it, especially Huygens and other proponents of wave theory, that this is the speed of light, and it is finite. I'm actually not going to discuss how to exactly compute it. There are articles on the web, you can read how to compute speed of light from this phenomenon. There's another book that I have, it's on the history of ether and light and electricity and magnetism. So I can send you extracts from that book, you can use that to understand the computations. But that's not our point. But anyway, shortly after this, another more convincing measurement of speed of light was made. And that was done by Bradley. And he was also an astronomer. And his interest was also in something else. What he was trying to do, he was trying to prove the heliocentric model of universe. That sun is at the center of the universe and planets are going around it. It's around 1700. So his time was 1693. So he was trying to test one particular prediction of heliocentric universe to prove that sun is really at the center of the universe, as opposed to the widely held belief that Earth is at the center of the universe. The people who were in favor of Earth-centric universe, they argued that suppose sun is at the center, so Earth is going around it. And let's say you're looking at a star here. So if you want to imagine, please imagine it like when the star is here. This is the plane of Earth rotation and the star is somewhere here. So they say that if Earth is revolving like this, when you observe your star from here, you point your telescope like this, here's your star. And when you are here, you point your telescope like this, and both of these angles would be different. Right? Makes sense? But they say we measure the position of any star in the sky from within 1 year, either in, let's say, December and June or September and March, we see the star to be at the same position.
Isn't that because the star is very far?
That we came to know later. But at that time, people thought that the distance is not that much. So that was, and especially they also knew that the distances are different, because some stars are bright, some are wide. So that thing they were right, that the stars are different position. So this man Bradley tried to measure the position of this Gamma Draconis. It's quite bright star in the sky. And he thought that if I make precise enough measurements of position, of angular position of my telescope at the time of June and December, I should be able to see the difference in angle. So let's say in December, your angle is beta, this is telescope, and in June, the angle is alpha. So he wanted to measure at December and June because this star is in this plane, June-December plane. That people knew because in June and December, you have to align your telescope in the same direction in respect to Earth. And when you are in September and March, then with respect to your position, it's rotated by 90 degrees in this plane. So in June and December it was aligned, but in September and March it was rotated by 90. So he said that in December and June my telescope I can measure beta and alpha, and from that I will see the difference, and that difference will be able to tell us, will be able to prove this thing. It's called stellar aberration, that the star should be at a slightly different position. He did the measurement for a whole year and actually repeated again. He didn't see any difference between beta and alpha in those 2 months. But he did see quite a lot of difference between these two angles in September and March. That was initially perplexing for him. That where I should see them to be at equal angle, I see them to be at a slightly different angle. Where I should see them to be at different angle, I see them to be at equal angles. So to explain this, he hypothesized that speed of light is finite. And he measured speed of light, and actually came pretty close to what we even have today, about 189,000 miles per second. So let me quickly show you how to measure it. Because his measurement of speed of light were based on this assumption that light is made of a stream of particles, and the Galilean law of relativity applies. In Galilean law of relativity, if you have something, let's say, going on with speed v1, and you have something other which has speed v2 with respect to this, then the speed with respect to this thing is, this sign you have to work out if the direction is same or opposite. So this is the Galilean or classical law of addition of velocities. He used this one, and the idea that speed of light, the light is made of particles. So how we did it? He said, now let me label this thing as, let's say, September, and this is, let's say, March. So he said that suppose speed of light is c. So it has, we call it x. Let's call this z. So it has an x component and it has a z component. Let's say this is cz and this is cx. So in September, the velocity of light with respect to Earth is what? Let's say velocity of Earth is u, and it's going towards the star with velocity u. So it means light is coming down with the velocity component cx minus u and cz in September, say, and in March, since Earth is going away, the component of velocity are this.
Sir, ये angle telescope की angle of elevation है।
जी।
वैसे तो अर्थ का tilt भी तो होता है। जब आप वैसे complete करते हो अपना year, so let's say अगर आप 180 degrees apart हो, तो वो अर्थ की tilt की वजह से तो वैसे आपको जो sky
तो वो जो चीज़ है that people had already been able to factor in, because that's quite a lot. So actually 24 hour, your position of the telescope also changes. So this is with respect to one reference, either let's say maximum or minimum. So that 24-hour diurnal motions, they have been factored in. I'm just trying to keep it simple. So all these things, because astronomy was quite advanced at that stage actually. So these positions and these things, they were already worked out. So it means this angle beta should be, tangent beta should be, is it this over this one, cz over cx minus u, and tangent alpha is CZ CX plus U. And if you work out, let's say, tangent beta minus alpha, and let's put this thing CZ CZ square CX square minus Q square. You take LCM and simplify it and you get to this expression actually. So this one. And if we assume that velocity of Earth is much smaller than velocity of light, which it is, and actually velocity of Earth was known at that time. So you can take it upside and open it binomially, and you can approximate it as U over C, CZ over C. And this is tangent beta minus, since this is extremely small, so you can write it like this. So now in this equation, this is known because this can be found from angle in June, because the velocity towards or away from that star is 0, so it's simply CZ over CX. So from the angle in June or December, you know this ratio. This he has measured in September, and this U was known, so he computed C to be roughly 189,000 miles per second. For reference, this currently accepted value of 2.9 and something 10 over 8 meter per second translates into about 186,000 miles per second. This is pretty close to what we have today. Given that the telescope angle measurement things were not perfect, the knowledge of U was not that accurate, but still he was able to measure it quite close. And this was, I think, done in about 1740s, 50s. Okay, so this was the derivation of Bradley by assuming that light is made of stream of particles. And that's why he was simply able to invoke this thing. Because you can then just imagine light to be made of some balls, and people already know from Galileo how to add velocities, so you can do this. If you assume light to be wave-like, with the ether everywhere around Earth and universe, then the calculations are different. And actually, Fresnel then did those calculations by assuming that Earth is going around in a sea of ether, and then he did, later on, he actually did calculation on wave-based theory, and he found the speed to be the same as well. So he explained star aberration because of finiteness of speed of light, and he also computed it there. But the first measurement of speed of light on Earth, with everything on Earth in one reference frame, was done by Fizeau. Actually, there is another person, Arago. He did an experiment before him. I'll come to that later because This experiment was done in 1849 by PHY. To measure the speed of light. And he actually had a very ingenious idea. What he did that he had a source, and then he had a lens. I'm drawing the lens like this, which converts this diverging beam into a parallel beam. But what they had was a combination of lenses, so that this color dispersion and other things can be eliminated. And sometimes the symbol you will see in optics literature is like this. This actually represents a compound lens. But I'll just use the symbol for simplicity. So, no, we had a mirror, partially silvered mirror. So after going through this, we get focused here, and here he put a saw. And then a mirror. So this is a point source, light is coming out, and this after going through this partially silver mirror, it's let's say focusing at this point, and then this is a toothed wheel. So if you look at its cross section, it's like this. Okay, so there's empty space and the steel and empty space, and he focused this light just right at this point. That if we moves, it periodically falls on this empty part and on the tooth. And then it goes through this lens, travels, and is reflected by this concave mirror. So now, let's say this wheel is rotating with a known velocity. So this light that comes here, when it passes through this one, so part of it will pass through, right? And then it goes like this, and by the time this light comes back after reflection, the wheel might have moved a little bit, so that when the light went in, there was this part, and now when the light is coming back, maybe it's this part. If you can set the speed in such a manner that when on the way back, you do not see any image here, let's say it's dark, then this round trip time is either equal to 1/2 period, or 1.5 period, or maybe 2.5 period, and so on. And you can actually determine exactly if it is half period or 1.5 period by simply starting from a very small velocity. Because when you are rotating it just slowly, you know the light is fast enough that you are getting a bright image here. So if I plot a spectrum of intensity at f versus speed omega, initially we will have a bright spot. But as the speed is increased, the intensity will begin to decrease. And at half of this time, it will be the minimum darkness, and then it will begin to increase again, because it is moving so fast that the light that went when it was here, and by the time light came back, it has moved by 1 tooth. So you can make a plot, and you know this frequency, and you know this distance. You can measure the velocity of light much accurate. And he actually didn't have to have a lot of stuff. This distance was only a few meters, and he was able to measure the speed of light, and he found it, unfortunately, to be quite off. It was 194,000 miles per second, which is it was even off from the today accepted value, but more than what Bradley's got. And can you see why? Why?
It's passing through mirrors, right? I mean, isn't the speed of light different in a different medium? I mean,
Yes, that's a good point. But you can consider that fact, so that's not a big of an issue. And since this thickness is very small as compared to this one, the effect would be little, but yes, that's one reason. But major reason, as he also recognized, was this, that it wasn't easy to locate this minimum point exactly. They didn't have many photometers at that time that this plugged to a computer and you're getting this nice shape. What you are doing, you are at best have photographic plates, and at worst you are just looking at the image and trying to find the intensity. It's 1849. The best thing at that time to measure these intensities of light were just photographic plates. Even with that, he was able to find that velocity of light is this. So the major issue was actually this. You have a continuous spectrum where you have to find one point. And almost any experiment in science where the situation is like this, that you have to take one point out of a continuum, the error is usually much more than performing a null experiment. More sensitive experiments in physics are usually null experiments. That the value that you are looking for is something where either something goes like this or something goes momentarily down. That's easier to spot, either sharp tips or sharp peaks. So this was not a null experiment, but this idea was used by other people to construct null experiments to make better measurements of speed of light. And actually, the next modification of the same thing was done by Foucault. So what Foucault did, let me erase this thing because I think that would be quicker. He removed this thing and he took a rotating mirror at that point. So you have, so actually I think there was a focusing lens missing in this background. So there should have been a focusing lens here. So the light that was going from this, he converted them into parallel beam, and then we simply put a mirror here. This is its pivot. This is a concave mirror, and then the light moves back. So this is his principle. So let's say this mirror is stationary here. So what's going to happen? This source is going to be imaged at this point F. Right? Light is coming out, this is partially silver, it's diverging, this makes a parallel beam, it's reflected from here, comes back, goes back here, gets reflected from here, and is focused at this point. Well, let's say this mirror is moving now. You have one reference point, let's say. And then you begin to, so this is a mirror like this. For example, this is a mirror. So let's keep it this. And this is rotating like this. Or you can say like this. So imagine like this. So what happens that when light comes here and it's reflected from this point, say this is its position where it is just reflected. If it is rotating, by the time this light comes back, the position of this thing would be something like this. So it goes slightly differently. So it's reflected from this and focused to a different point, F'. And this shift in this position is proportional to the time that is taken by light from this point to this and back. So now in this experiment, when you, let's say, have some scale here which is graduated, all you have to do is just measure the shift. And actually, it won't be just a shift of point, it won't be a continuous spectrum. Continuous line here, light line. Because this is continuously moving. It is not that when light came here, it went there, because there was more light coming when it was going slightly there. So you will see a continuous light line here. So this experiment was easier to set up and the experimental error was smaller, even though the concept was same. He measured this distance and then from this geometry, he worked out the formula for speed of light by considering the speed of this rotating mirror. And his value was much better. It was actually 2.98. And not only that, Foucault was able to give the uncertainty in his very nice.
There was the mirror double-sided.
No, it was only one side. So there's no reflection. You can make it double-sided, that will only increase the intensity here. So this was actually pretty good at that time. For this measurement, you actually don't even have to assume if it is wave or if it is particles or whatever. Because it's in one frame of reference. There's no extraterrestrial frame which is moving with respect to Earth. Source and measurement points all are in one laboratory frame. So this measurement is independent of the nature of light. And the only drawback of this technique was this, that you can't improve the uncertainty in the value too much. Because to improve the value, you have to increase this width so that the uncertainty that you have in reading these two, taking these two measurements of this point and this point, its effect can be reduced if this length is increased because relative uncertainty would decrease. But for that to happen, this mirror has to go away even further so that it takes more time. But since it's a concave mirror, light spreads. As you take it away, the intensity of image here decreases. So it's a trade-off. And when the intensity decreases, the reading becomes even more difficult. So this was the best that they could do. And for the next, more sensitive measurement, the idea has to be changed a little bit, and that was done by Michelson. And it's not his that famous experiment, which we will discuss later, about the detection of ether. So what he did was to make the experiment even simpler. He says let's have a point source here. Light goes out. You have a fully silvered mirror. The light is reflected. You have then, so essentially it's diverging. A mirror which makes into a parallel beam. And then you have a plane mirror. Since it's a parallel beam, it reflects it back. And this mirror is actually rotating, so the image will be at some other position as well. And since this is a parallel beam, you can take this distance to be almost as much as you want, even though there is some spreading of beam as well, even when it's a so-called parallel beam, because it's a Gaussian beam. So you can take it to infinity, but instead of having few meters, as for Physio and Foucault, he was able to take it to few miles, I think 2.2 miles. Long tube was constructed for him to do this experiment. So, and in Physio's and Foucault's experiments, the deviation of 2 points were around few millimeters, I think about 3 millimeters. That's the maximum they could get. And Michelson was able to get this deviation of about, I think, 133 millimeters. So compare this to about 3 millimeters. Your uncertainty goes down by about 100 times in the measurement. And he not only measured the speed of light in air, like he had constructed a tube, so regular air, they also evacuated the tube to 1,000th of a torr, and it was almost a vacuum for all practical purposes. And then measured speed in vacuum as well. So his speed in air was air and vacuum. That it was so sensitive experiment that it could differentiate the speed of light in air and vacuum. And actually, along the way, I forgot one important thing. Another experiment that has settled the quote-unquote settled the debate whether light is vertical or wave by measuring the speed of light in water. Physio's experiment. So let's come back to this experiment. So here, what you can simply do, you can construct a tube, right, and fill it with water. So if your speed, for this, you don't even have to measure what the speed exactly is, but even though they did, but all you have to do is to see if the speed of light in water is smaller than speed in air or larger. If this shift becomes smaller after inserting this water tube, it means the speed of light in water is larger. Sorry, the tube is at wrong place. The tube has to be here. The tube has to be between this part. So if the speed is larger, it means it comes back quickly, so this shift is smaller. If speed in water is smaller, it means it takes more time, so this shift gets smaller. So they measured speed of light in water, in still water, and found that speed of light in still water is smaller than the speed of light in air. Not only that, they measured the ratio, and that came close to the value of refractive index, which you measure differently, which comes from the ratios of angles of incidence and refraction. So these two things coincided with each other. And actually by this time, around 1850, you can say like 99% people in scientific community started believing that light is a wave. Especially after Maxwell and Hertz's experiments, the debate was almost settled, except few lingering things. And the most important of them was ether. Because it required it was supposed that you need a medium for wave to propagate.
So if the speed of light and water is constant, this is like real?
Yes, it should increase. Right? Because it fell, this distance is proportional to the time that light takes to go from here to here. Okay?
No, between F and F'.
Yes, but this distance is proportional to the time that light takes to go from here and come back to this point. So if it is more time, then this length will be larger. Any question or comment?
वैसे ये क्यों पता है कि wave है या
Because it satisfied, this hypothesis satisfied all the observations. For example, you can explain polarization with particle nature, with streams of particles. You can explain why don't two beams of particles don't interfere. They seem to pass right through each other. Plus, actually by this time there were a lot of experiments. For example, there is another experiment of Arago, because I think one of the presenters was presenting his idea, Huygens I think it was, that light is wave. So somebody pointed out, probably it was Poisson, who was a mathematician by the way. He said, this can be true, because if light is wave and you have a circular aperture, and if you shine light on it, on the other side, you should see a bright spot at the center. It's called Poisson spot. You have this circular disk, light is coming from this side. It doesn't matter if it is a hole in sheet or if it is a disk and everything is empty around. It doesn't matter for this experiment. Because the idea was this, if this is wave, at the point on the center on the screen, since the phase difference in all the waves that reach from this radius, they are going to be there in phase. So there has to be a central bright spot. Hota hai, and Arago actually did that experiment and found that Poisson spot as well. Sometimes it's called Fresnel's spot as well, or Arago spot as well. So there were actually a lot of things that were all pointing towards wave theory of light.
But none of them said that particle nature is not possible. It is just said that wave nature is more like wave.
They should have said that, but actually the people have been even quarreling over this, especially and sometimes personal attacks as well. Because those scientists were human as well. Okay, so there were only, I think, objective in scientific discussion as we are, and totally irrational in our private life. Anyway, so let me just discuss. We still have time, right? Okay, yeah, fine. So let me just recap and try to tell you the path ahead. So Bradley discussed our aberration based on composition theory, but Young re-explained that stellar aberration using wave theory, and but he had to make one assumption to explain that stellar aberration, and that was that different objects have different densities of ether. Now, until Young, until about 1800, people have this notion that ether permeates all space, even inside the bodies as well. Ether is everywhere. For example, I move from here to here, so there was ether in me that is now gone there, and there is ether that has come from this side to this inside me. This is one concept. Or you can say that I'm simply displacing and ether is coming from here, or you can think that, okay, there's ether everywhere. And when I am moving, only I am moving. The ether that permeates me is simply there. So the density of ether is the same everywhere. That was the initial concept. But then, since new things were coming, especially star aberration, and also this idea that why speed of light is different in different mediums. For example, in refraction. So speed of light, we now know that here is different, here is different. So Huygens proposed that let's assume that density of ether is not same in everybody. But the density of ether is proportional to the square of the refractive index in that part. So that with this assumption, since you're still thinking in terms of sound waves as well, you can explain the speed of light in rarer medium is fast and in denser medium it's slow because ether is more dense. So now here is this concept that different bodies have different densities of ether. Now then this begs the question that when I move, what moves? Does all the density of ether that is inside me moves with me, or only a part of it that is more than the background or vacuum ether density that moves with me? It's called partial drag, and that was the hypothesis forwarded by Fresnel, that when a body moves, the excess ether that is present in the body, only that moves with it. For example, let's say the background ether density is 10, whatever 10. And let's say my density is 12. So when I move, only 2 moves and 10 remains stationary. And this actually has implication for measuring speed of light when we are in moving references phase. Because then we have to see if, because people were trying to use Galilean velocity transformation law, if you want to use c plus u, if u is my velocity and c is speed of light, if I'm moving and light is moving inside me with speed of c, what speed you should measure? Should you measure c plus 2? And you should if you assume that all of the ether is moving with me. If only partial amount is moving, you can say c plus fu. F is the fraction of ether that is moving with me. So that was the hypothesis of Fresnel, that only there's a partial drag of ether. And then there was another hypothesis by Stokes. He says, no, the full ether moves, but when I move from here to here, this ether, let's say, go there, or this ether is displaced and something comes from here or whatever. Even though you are explaining all these flows, but you're still assuming no disturbance in background ether. Because otherwise velocity of light could go like this. So in the next lecture, we will discuss the idea of this ether and how this was used by people at that time to explain one very important experiment, and we will discuss another of his used experiment where he measured speed of light in moving water. And astonishingly, not astonishingly, but perhaps more surprisingly than this one, speed of light in moving water was different than in stationary water. And the difference couldn't be explained by the Galilean law of velocities, at least. It wasn't simply c plus u, if u is velocity of light of water. And it was not also c by n plus u, like n is the factor. So this is actually speed of light in water. So it wasn't this. And it wasn't also, let's say, you can put n here or something else. This was explained by the partial drag of Fresnel. We will do that. But that actually raised other questions. And that's what we will discuss. In the final 1 minute, let me just describe one other experiment that people set up to see if light is really made of particles. So after Newton's hypothesis, people at that time believed that the speed of light that is emitted by a star should depend on, let's say, its gravity and also on its speed. On its speed, you can see logically very easily, because if this is going with speed u and something is emitted with speed c, the speed of light should be, let's say, c minus u. And they assume that, okay, it depends on its size, because the light is getting out, so maybe there's different force of attraction that's giving it different speed. There was one man, forgot his name, he tried to test this thing, that let me see if really the speed of light that is coming from different stars is different or not. He simply put a prism after his telescope. So when he focused on one star, light gets diffracted, he measured this diffraction. When he focused on another star, he measured the diffraction. He focuses on sun, he focuses on moon, and he measures the diffraction. He says, if the velocities are different, then since this dispersion is dependent on relative velocities of light here and in glass, the dispersion should be different. But they all gave the same dispersion, and there was only one conclusion, that speed of light coming from all different stars moving in all different directions is actually the same. But people were still able to invent ideas to explain that maybe corpuscular theory is right, and perhaps stars are emitting light particles with all of different velocities. But what we are able to see with our eyes only falls within a certain range. So that's why what we are measuring is only a portion of light, and maybe there are other lights that have different velocities. So this was struggle because of the widely held belief that light is made of corpusculars and not wave. So next discussion would be on ether, and we will hopefully get to the special theory of relativity. Thank you very much.